Hello, welcome back folks. I'm going to do ionization energy, okay, today, the first and second ionization energy. I did this video actually last week and it won't upload. YouTube doesn't want to upload my video. I have no idea why, so I'm having to redo it. Anyway, ionization energy is a measure of how easy it is to remove an electron from an atom, okay? So basically it's how easy is it to pull an electron off an atom. That's what it's measuring. It's the energy needed to remove 1 mole of electrons from 1 mole of gaseous atoms. So that's when you heat atoms and put them into the gaseous state, basically they're ionized, they're vaporized. So it's the energy needed to remove 1 mole of electrons from 1 mole of gaseous atoms, which is called the enthalpy change, okay? Given the symbol enthalpy change I've written neatly here, the symbol delta H, okay? The units kilojoules, capital K, capital J, kilojoules units, okay? So an example is if you take an atom, can be any atom, I've written Na here, it could be any atom though. So atoms are ionized, that they're heated and an electron is lost from the sodium. That's the gas state, that should be a G there, so a G. Okay. And the enthalpy change is 502 kilojoules per mole. The reason I've written 496 is I was going through the data booklet for this, which is this, and yeah, so you turn to your data booklet, okay? So yeah, advanced high data booklet, and you go through the pages until you find the table of ionization energies, okay? And if you take the elements, okay, this one, sodium, the first ionization energy is actually recorded as 496, okay? The reason why I've written 502 is because that's coming from the textbook. The values do vary a bit because they're actually averages, they're not fixed. Different experiments will give slightly different values. They might be the same, but they're around about 500 kilojoules for the first electron, first ionization energy of sodium, okay? This is the first ionization energy, okay? There's the electronegativity scale I mentioned in the other videos, okay? So yeah, it's the energy this is the energy needed to remove the outermost electron from sodium, okay? The second ionization energy is for sodium is 4,562 roughly, okay? In this data table it's 4,562. It's about 10 times, 8 times that value, okay? 9 times that value, okay? So yeah, that's the energy needed to remove the second electron from sodium, okay? Again, you write the units after it. It's amount of energy per mole, okay? You must always write units after numbers when you're dealing with energies or lengths or volumes. Always write the units after the number, because a number with no units has no meaning, okay? This is a measure of energy kilojoules per mole, because it's dealing with 1 mole of atoms and 1 mole of electrons, so you must write the total amount, the number, the size of the energy plus the units, kilojoules per mole, okay? Otherwise it has no meaning. In the exam I don't think they always want you to actually write the units, because the questions will know what it's about. Your teachers will advise you, but I don't think in the exams they actually demand units. But if you're generally doing calculations, if you want to go on and do careers in chemistry and do chemistry degrees or go into jobs in chemistry, you must always write units, because otherwise the number has no meaning. Even if you written delta H, simply writing this is not acceptable. You must write this as well, okay? So that's the energy needed to remove the second electron from the sodium atom, okay? So the symbol of the units, kJ, kilojoules, is actually named after this chap, okay? 19th century scientist who first worked on this sort of problem of energy, okay? He discovered the first laws of thermodynamics, okay? And he got this thing. There's other videos about that. The ionization energy trends, okay? So as you go from periodic table, as you move from top to bottom, okay, the ionization energy drops, okay? As you go from left to right, it increases, okay? Why is that? Pretty simple, really. It's a bit similar to covalent radii. It's the same sort of reasons. It's the same as why the covalent radii increases. Well, actually, the covalent radii increases as you go down and decreases as you go along, but it's the same sort of reasons why it happens. So as you go from left to right, the reason why the ionization energy increases is because the nuclear charge going along the row gets bigger. The number of electron shells stays the same. Okay, there's an increasing number of electrons, but the number of shells stays the same. So the nuclear attraction and pull on the electrons gets bigger and bigger. So it becomes harder to pull electrons off, okay? Whereas when you go down, although the nuclear charge is getting a lot bigger, the number of shells is also increasing. So the outer shells here have many more shells within them, inside them, which shields the outer shells from the nucleus. So it's very easy to pull electrons off it's very easy to pull electrons off atoms as you go down the periodic table because there's very little force from the nucleus pulling at them, okay? So that's why as you go from top to bottom, the ionization energy drops. As you go from left to right, it increases, okay? And this is kind of a little diagram to explain that. So when you go from left to right, lithium to fluorine, there's still two shells, but the nuclear charge is getting bigger and bigger. These are all positive. So there's a stronger pull on the electrons, it's hard to remove them. But if you go downwards to cesium or francium, although the nuclear charge is going up, there's far more shells, so there's a lot of shielding protecting this electron from the nuclear charge, so it's very easy to remove it, okay? Okay? So yeah, another example of ionization energy. I also, what's I going to do? Yeah, if you also so if you add the first and second ionization energies, okay, that's the energy needed to remove 2 moles of electrons from 1 mole of atoms, okay? In the gaseous state, okay? So when you add up the sodium values, the the first ionization energy is about 502 kilojoules per mole, and the second ionization energy equals 4560 kilojoules per mole. Okay, so those add those together, you get 2, 6, 10, 5. Okay, 2, 6, 10, 5, 2 is 10, 4 is 5. So this is the amount of energy needed to remove 2 moles of electrons from 1 mole of atoms in the gaseous state. Okay. Another example of ionization energy is potassium. Sorry. Plus electron. Potassium has a first ionization energy 419. Okay. You read that there. See, that's so you write that enthalpy 401.19 kilojoules. Another example would be, say, take calcium, you could take magnesium, okay, 738. So if I take magnesium, 738, okay. So sorry. I'll scrub that aside again. Okay, so magnesium gas goes to magnesium plus gas plus electron, and normally you write this straight afterwards, but this is slightly running out of space. It's because my pen's thick. If I was using a Bayer, I'd be able to fit this in more easily. That's why. So maybe write it here. What did I say for magnesium? 738, okay? So 738 kilojoules per mole. Okay? Yeah, normally you write it all in one line, but this thick pen is stopping me doing that. So yeah, so that's basically what ionization energy is, okay? Do you want to write down, so the first and second ionization energies of a boron and oxygen, of oxygen atoms. Can you do that? Pause, and then I'll write the answers down, okay? Okay, the answers now. Boron, so equals boron plus electron, okay? Making a mess of this. So first ionization energy equals 801. I'm making a mess of this. Kilojoules per mole. Sorry about the mess. And then the second one, what's the second ionization energy? Boron is 2427, okay? 2427 kilojoules per mole. Okay? And then oxygen, okay, so oxygen is gas, comes oxygen. Normally oxygen doesn't actually lose electrons, but you can write it like this. They do have values, so I should say the reason why the second ionization energy is much higher than the first ionization energies is because once the first electron is removed, the second electron is usually further to it's closer to the nucleus. Okay, it's getting a much stronger pull on the nucleus. Okay, it's receiving a stronger pull from the nucleus, so it takes more energy to remove it. Okay, and then oxygen. Equals 3,389. Okay, so that's ionization energies. Bye for now.